Okay, good morning. So first, very quickly, thanks a lot for those of you who filled out the survey. About 50 or 60 of you did that, and you gave a lot of feedback. Some items are very easy to address, and so I did that. The pre-labs now due on Sunday. Of course, most of the pre-labs... Hey, can you quiet down a little bit? Okay. Of course, most of the pre-labs have been due already. I thought that I could not assign anything that was due on Sunday. In the past, I've gotten negative feedback on doing that, so maybe this time it's different. Webcast, the delay. I did remove the delay. You know why some of my colleagues do not even bother with the webcast. And you do know why some classes and some webcasts have a delay. So you can control that too. Homework. I did get a lot of comments on the feedback system, the online system. Lots of suggestions how to make it better. Apparently there is a system in physics that has many more capabilities. I did look at that. Unfortunately, there is also absolutely no way for me to duplicate that. So anyways, I decided to switch back to paper homework. So from now on, we'll use paper homework. What? My rationale for paper homework is that I got a lot of very valid comments. For example, the online system, it gives you feedback wrong, right or wrong, and nothing in between. I totally understand that is not very encouraging. Some of you outright said in the feedback that heck, this online system is so discouraging, just get rid of it, this is total junk or whatever. I mean, so I really got the impression that, yes.
Do you have an option, like you can turn it online if you like the online system?
No, I'm not. Doing the online system is an incredible amount of work on us. Because as you notice that if there is a bug in the online system, it affects you very badly, right? If one of the solution equations in there is incorrect, then all of you, 150 of you, are going to spend hours and hours, and of course you get upset, right? So we have to do almost actually truly a double-blind checking. I make the solutions, the TAs, they go and check it, and for every problem where they don't get the right answer, we'll have to go and fix that. We'll have to have somebody, a third person, check it and so on. It's a lot of work to make this online system. So you got to decide what you want, but we can't have both. Yeah.
So for paper homework, we don't have a second submission?
Well, of course not, right? And okay, so show of hands. Who would like to continue the online homework? And who does not want the online homework? Okay, so maybe it's just that the voice of one group was stronger than the others. All right, so I'll revert that in that case. So, but again. I do appreciate some of the feedback that I got. It does have flaws. It's not perfect. I totally admit it could be made better. I don't have the time or the effort or the imagination how to make it better, and so you have to live with the flaw if you use it. Okay. About the lectures, lots of comments there too. More examples, more explanation of concepts. We have to be very efficient if we want to do all of these. More interaction. And I like this one. I should be more like Babak and Dave Wagner. I'm not oblivious to them, and I do talk to them, and I do admire their ideas and so on. Of course, I can't be just them, right? And they did not offer to teach EE40 for me. I was, but they don't. So, pace, of course, sort of in the middle, right? So if it's too fast, well, yes. 3 submissions for everybody. Okay, so the number of submissions on the homework, of course, when it's online, is totally arbitrary, right? I can make it 10. In fact, in the past, it used to be 5. But there was no feedback on all 5. It was only the last 2 that you actually got feedback, which answers were correct and which were wrong. So my thinking was a little bit, as an engineer, I cannot go and sort of do this almost, well, try, does it work? Oh no, the airplane crashed. That wasn't a good try. And then try it again and so. Of course, this is not airplanes that are crashing, so it's not maybe a quite fair comparison. The other thought for me is that if you keep trying and you solve this problem for the 5th time and you get still a wrong answer and so on, maybe that's not a good use of your time. So again, for me, if you really feel that you learn more and it's a good use of your time, if you try 5 times, as opposed, for example, going to see help in the office hours, I can do that, right? For me, really, what matters is that you learn the material. It's a number somewhere that I can change. I can't change it only for everybody. I cannot say, well, you had there was something on it. I cannot do it on an individual basis. There's just no feature. The feature is not available. Okay, so is that who feels that he or she would learn more or better or would be a more useful system if we could have 5 submissions? I turn on the feedback, presumably, because I got so much negative feedback of no feedback that if you don't want the feedback, just don't look at it. Okay, that's easy. So who would like 5 submissions? Thinks that it would truly be better 5 submissions, and who prefers the present status quo? Okay, so I guess here. Again, so please do not complain then, hey, I'm really doing a lot of busy work here because I just had that sign and now I waste so much time trying to get that idiotic sign right? So there is a point at which it becomes inefficient. Your time's worth something too. Actually a lot, right? Yeah.
When you make it like 5 attempts, would you raise the level of difficulty?
Not for the homework. I'm not going to create all new homeworks. It's a lot of work to create these homeworks. As all the flaws they may have and so on, it would be the same homework. But be aware of that. Sometimes I get questions like, ultimately, if I make so, for example, one of the things I'm going to do is I'm going to drop one of the quizzes and so on, right? But ultimately, when I do too many of these things, they become not useful anymore to be part of the grade. And actually, some of you suggested homework shouldn't even count for the grade. That's okay with me, but again, somewhere, right? We have to have grades, and somewhere I got to get this information from. So ultimately, I have only the exams. And then you're under high pressure there too, maybe even worse than in the homeworks, right? So think about that, right? Plus also it's a little bit of a zero-sum game because Berkeley classes are not, you won't get classes in engineering where everybody gets an A, right? So we make the classes hard enough that the average is about a B-, in fact, in these classes. So if I make it easier somewhere, then it's probably going to be harder elsewhere. Right? Yeah. Right? Yeah.
Could you consider maybe dropping one of the pre-labs or something at the end? Because I remember for the musical notes one, there were 8 or 9 different submissions in a row.
Mm-hmm.
If you got the first one wrong, like calculating the resistors and the tones, then you got all of them wrong. And there were only 2 tries, so if you didn't try.
Okay, I can do that. For the pre-labs, one of the big reasons. Honestly, one of the big reasons why I make it part of the grade is that some of you, I know it's not you and not you and you, but some of you will prepare for the lab only if it's part of the grade. And if you're not preparing for the lab is a waste of time, right? And you're not learning much. So Yes, I can do that. So, all right, so that will be in the final grading equation that I will modify. Right? It's an Excel sheet. I somehow will figure out a way. Yes.
Last question. So for the 5 submission scheme, would you give us 2 feedback or 5 feedback?
I will be feedback for everything. It will be just five times. So again, it's up to you to decide if after the third time you still just get this cross, no, this is not right, whether now it's a better use of your time to maybe go and ask somebody, a colleague, a GSI, me, or whoever, right? Or on Google, I think you can even ask questions. Whatever, whether it's a better idea to get help, or whether it's a better idea to calculate it yet another time and maybe not finding the error, right? So that may be a lot of waste of time on your part, and recognize that, right? Don't waste your time. The point is not to get all the points. The point is to understand something. And if you don't know where the problem is, well, then it's really just busy work. So don't get into the rut of doing busy work. Okay, so all right. So I got all of that feedback. I hope the TAs are here to help me remember everything. The discussions. Actually, what was this? So homework, too easy, too hard. On the hard side, hey, you know, some of the stuff is hard, right? Circuits aren't exactly easy, so some of it's going to be hard, and too little, too much, rather too much. Again, with the online system, I can easily give optional problems, but of course, all this optional stuff somehow, in one form or another, makes it on the exam, and so you may want to do much of that homework, whether it's too much or too little, right? So too abstract. I'll try to make it a little bit. The text. Many of you do not like the text. I also made, unfortunately, a few discouraging comments that I personally feel that the text is too mathematical. I'll try to do something about it. You won't believe how much work it is to write notes. Labs. Most of you are learning from the labs. That's great. There are also many comments. Instructions are confusing. I always ask yes.
Yeah, for example, in was the last lab.
Yeah.
In the 2 diode problem before the one with the frequency changes, measuring the sound.
That was the audio, the synthesizer.
That one didn't clearly label that some of the cross sections wasn't connected, and other ones that were connected had a little bubble in it, but wasn't clear. So
no, that's
okay.
standard circuit diagram procedure. There's not a bubble there.
Yeah, before that, but there was never used for it, but suddenly appeared.
Yeah. Okay. So I'll see if I can make that a little bit clearer. The thing is that the schematic capture program, it puts it out that way. And as your colleague said, this is sort of standard. So maybe a comment there. So in general, this stuff, the instructions are confusing. Well, I do ask students also, some of the TAs actually of this class now, they have been taking the course, and I ask them what could be improved and so on, and they make me suggestions. But really I depend on your suggestions, because not the same thing is confusing for everybody, right? And so if you find something confusing, if you can help me by explaining what is confusing, then I may be able to try what might be less confusing. More design. Okay, I'll try to do that. On the other hand, also you realize design is not trivial, right? I could have said in lab 4, hey, now you sort of know what a 555 timer is. Go and design a synthesizer. More lab GSIs, you know that we are broke, not broken. Broken components. Again, if you have something that's broken, that don't just put it back, right? In the past, we used to be able that everybody at the beginning of the semester gets a bag full of fresh components that came new from the manufacturer, and they generally do work. Unfortunately, somehow that doesn't work anymore. Broken equipment, same thing. If you find something's broken, make sure somebody knows by the time you leave the lab room, because there is just not enough. We cannot have staff checking out all the equipment between laboratories. Okay. Survey, the discussions, they seem to be generally accepted. Again, you will have to realize that the opinions, they vary, right? It seems to be that a little bit more people, they like problems solved in the discussions, but some of them also would like to see more concepts. So you will see some kind of a mix of the two, and hopefully there is something for everybody, but it's not, of course it's not really personalized. Okay? So again, thank you for the feedback, and you gave me some more. I'll try to react on that. If you have other feedback, you can either pass it directly to me, or if you feel that that if your other would not, then you can also let the TAs know, or maybe a friend, or whatever. You can also try to get it anonymous to me. If it's constructive, I will try to do something about it. Okay. Where have we been? Okay, so we're talking about digital circuits, and we talked about these little blue things here. What are these? They're gates, right? This would be an AND gate, an inverter, and so on. Anyways, gates. We did synthesize just an adder out of such gates, but of course, the truth table would get much larger. We could synthesize a multiplier. We could probably synthesize a divider. I've never tried doing that, but there are ways. Some people have figured out how to do that. A 20,000-foot view of a digital circuit is just like this. It's a huge sea of gates that are somehow connected in the right way. Okay? And we're going to use that in order to make some very powerful statements, or get some very global understanding of digital circuits without having to design everything. Okay? So we, for example, will be able to estimate the power taken up by a microprocessor, which of course is an exceedingly complicated digital circuit, without having to get into all the complication. So that's why this, first of all, this 20,000-foot view is useful, and secondly, why it's useful to look at these sort of trivial things, these gates. Okay? In fact, this idea that you can build just about any digital circuit just by connecting gates in the right way has a very powerful and interesting ramifications. In particular, there are things called gate arrays, which are chips that contain many, I mean millions of these gates. And they also contain switches, and you can set those switches by downloading a code into that chip. You can set these switches to connect the gates in a custom form. And so that solution is used to, for example, try out live new compression algorithms. You can build a video compressor on one of these gate arrays, and it runs real time. Why? Well, because everything happens in parallel. It's not like a microprocessor has to do one instruction after the other. It's really very parallel. You can try out a new computer if you want. If you have a new idea on a new computer with 13 registers instead of 16 or whatever, you could try that, and people do that. They build whole computers on these gate arrays. Of course, programming millions of switches isn't trivial, or is at least as tedious, if nothing else. So there are formal ways on how to do that, and there is even a course, CS 150, that teaches that. So if you want to know more about actually designing a little bit more than just an adder out of these gates, well, that might be a course that you could consider. Okay, so we go into a slightly different direction here in EE40. We're not going to design all these complicated digital circuits, but nevertheless, we're going to get some very interesting and generally useful information about them. Particularly, we are going to pose and then answer two questions. How fast can a digital circuit go? Okay? And again, because the digital circuit's made out of gates, well, the question is also how fast can gates go? And then the other one that, of course, is very important is how much power or how much energy do they consume? And how will this change in the future? Why is it important? Well, for example, if you want to start a company and somehow your idea needs a digital system will use power, you need to be able to predict how that power changes over time so that you can position the product that takes 3 years to develop correctly that's going to be competitive. Okay, so these are the questions that we're going to focus on now. Now, in order to really get insight on these questions, we need to look at transistors. And transistors, they are based on a material that is called a semiconductor. And I'm sure you've heard about semiconductors, and some of you perhaps know what it is. But let me try to give a qualitative, but nevertheless solid enough view of what a semiconductor is so that we can afterwards understand how it impacts, for example, delay and energy. Okay, so what's a conductor? Well, a conductor is a material that can conduct current. Well, why does it conduct current? Yeah, exactly. There must be somehow charges there, and they must be mobile, right? Usually those will be electrons. They could also be ions or whatnot, but the point of a conductor really is that there are charged particles, again, normally electrons, available that are ready to move if there is an electrical field or a voltage applied, right? And if we have an insulator, then of course we also have, it's made out of materials, so therefore out of atoms, and of course there are charges inside those atoms, but in an insulator, none of these charges is willing to move. The atoms, they grab solidly to all of their electrons, and the electrons just can't move around, and consequently no current can flow. That's really what conductors and insulators are in a nutshell. Now, what about the semiconductor? Yes? Band gap? Some of them have a large band gap, some of them have a smaller one. What in the world is a band gap? We're not going to get into that. But in a semiconductor, it also can have charges that move around, but the number of charges that are available to move around in a semiconductor can vary very wildly. It can vary from almost no charges that are available to move to having very many charges to move around. And so the number of charges in a semiconductor varies a lot. So a semiconductor can go all the way from an insulator, or almost an insulator, not quite as good as Teflon, but almost, all the way to being essentially a conductor. Actually, a reasonably good conductor. Not as good as copper, but reasonably good. And there are two ways on how to control the number of charges that are available. Anybody has an idea on how that's done in a semiconductor? Yes? Okay, so it's basically by playing with the material. For example, you can make the material dirty, although you have to be very careful and control what dirt you add. But by adding just the right amount of dirt, you can make it that there are more or fewer of these carriers available to move around. Okay, so far that isn't actually that terribly interesting and it's useful, but it's not that that alone wouldn't make it really nearly the useful material that it is. So what's the yes? Yeah, well, just in the semiconductor, it doesn't care whether the current goes one way or another. If you add multiple semiconductors together, then you get that. Yes? Yeah, the temperature also affects the number of carriers available. That's true. No, but I'll say... this is really the reason why a semiconductor is such an unbelievable material and why we can do all of these things. Electrically, we can control the number of carriers. So electrically, we can make this thing a good conductor, and electrically also, by changing the appropriate voltage, we can make it that it is an insulator. And because we can do that, we can make devices that control the current, for example, electronic switches. And the effect that we use to control the number of carriers is called the field effect. And there are some complications to it, but in principle it's very, very simple. So if we have a chunk of semiconductor, this is semiconductor, so for example silicon is a semiconductor, the most prevalent one used today, then we can have some kind of a plate. This could be a metal, it could also be another semiconductor, doesn't matter. And here there is an insulator. Silicon oxide is used very often as the insulator. Air could be used also, but then you will have floating stuff, right? A bit more difficult to make. Anyways, if we have such an arrangement, looks like what? It looks like a capacitor. Well, and of course, we've seen that with the capacitor, we can pump charges from one side or one plate of the capacitor to the other. And we can use that effect in the transistor to make it that there are, by applying the right voltage here, that there are suddenly lots of charges available to carry current. And so current can flow from this terminal to that terminal. And we can also make these charges disappear by applying the opposite voltage or no voltage. Okay? So that's really how a transistor works. There's more things to it, but we don't need to get into more detail than this. This understanding is going to be good enough for us to understand, for example, scaling laws. How do transistors get faster, or how do they use more or less energy when we make them smaller? Okay, and so we're going to go into that now. We're going to go and try to understand how much energy, or how much time our digital circuit takes, and how much energy it consumes. All right, so here is again this transistor. You will notice this picture here is exactly what we had on the previous slide, but it's now turned by 90 degrees. It's the same thing. Okay? So the point again is that by applying a voltage between this terminal and either here, or it turns out we can also apply on the contact slightly on the side, then we can control the number of electrons that are available to carry current there. Now, of course, this being an electronic circuit component, there is a symbol, and this is the symbol. And the terminals, they have names. They're not terribly important here. If you take 105, you will talk about source and drain all the time. But here, that's really not the main point. So now, let's try to construct an equivalent model. So we've already said that this thing here is a capacitor, right? So there really must be a capacitor between this terminal here, that's the gate, and this side down here, that is the source. Okay? So we will later see it's most unfortunate that there is this capacitor there. Most of the time, we really would rather not have it, but you also understand that from the function, from the operation of the transistor, there's got to be a capacitor there. You move the capacitor, you remove the means by which you can control the amount of carriers in the channel and therefore the conduction. Okay, so this capacitor is going to be there. And so here, that's the component that we put. When you put the transistor there, really what we're actually putting there is a capacitor between the terminal that's called gate and the another terminal that's called the source. Okay? And then maybe more interesting is there is the connection between this side here, that's called the drain, and this side here, that's the source. That's usually called the channel. And that's this thing where we can control the amount of charge available to carry current, and consequently, we can modulate the resistance. And a very simple way to put that is that we have a resistor that varies. Now, in digital circuits, we are going to, this voltage here between here and here, this voltage is going to be either VDD or VSS, right? And consequently, either we can arrange it with these transistors, we can make it if this voltage is 0, there are no carriers available here to conduct the current, and so there's really an open circuit. And we model that with this switch, okay? Then the switch is open. Now, if we apply a voltage here, VDD, well, then suddenly a lot of carriers start appearing in that channel because of this field effect business. Now current can flow, and really it's like if we have this switch closed. And what is also included in that model is that a transistor isn't a perfect conductor. It starts conducting. It can start conducting reasonably well, but it still has some resistance there. And in fact, depending on the type of transistor and the size and so on, that resistance can be anywhere from a few ohms to a few kilo ohms. Okay? So even when the switch is on, it's not a short circuit, it has some resistance. Okay? And that is important. Of course, ideally, would be great if this resistor was 0, then we really could run a lot of current. In practice, we have that resistance. We will see that causes delay in our circuit. The combination of capacitors and resistors, well, that causes delay. So now there is one other thing that we could, out of this picture, we can get. And that is the value of this capacitor, CGS. Well, it's a parallel plate capacitor. What does the capacitance of a parallel plate capacitor depend on? Well, it depends on the size of this thing, right? If I make it the area bigger, well, I get more capacitance. Well, in transistors, there is a nomenclature on how we call this size. This dimension here, the length through which the current has to flow from one side of the transistor to the other side of the transistor, that length is called the length of the transistor. So this thing here is L, okay? The channel length of the transistor. That's the thing that you actually read about when you read all these news about Intel came up with the 22 nanometer transistor or whatnot. That's what they mean, this L, okay? Yes. Yes. Well, it turns out the way the transistors are made, this part here, and this part here is always conducting. And it's only the piece under the gate where, using that field effect, we actually control the conduction. Okay? So that it's only that part. Very closely. Okay? So, incidentally, this is a very simple model of a transistor, but it's also a very useful one, as you will see. And of course, there are more complicated models. EE130 would go into much more depth on this. And 105 goes into a little more depth. Okay, so this capacitor, well, here I've drawn the thing from the top, so there would be the source and the drain, and the red stuff is the gate, and so this dimension here, again, that's L. And it's only the part that is covered by the gate. And how do they do that? Well, that's very interesting, but they have a way to make it that it's just that part that modulates the current. Okay, and then there is this other dimension here. It's a little bit like a bridge. Well, a bridge or a tunnel, right? If we make more lanes, of course, more cars get through. Okay? And we do that also in a transistor, but of course, if we increase this width, then the capacitance also increases. So the capacitance, therefore, must be proportional to this width and to this length. Okay? And then, of course, it also depends on other things, like the spacing in the capacitor, right, between the plates. I can't mark that anymore. It's a little bit messed up already, and so on. As a circuit designer, it turns out, when you become an IC designer, of course you have to design a real circuit, a circuit operation. But in the end, when you're done, on the day you're done and you're shipping your design to the fab, well, you've determined your values for W and L for every single transistor in your design. Okay? So these two quantities we actually can control when we make our chips. This quantity, that's the guy in the fab that controls it, and he just tells you, this process here that I'm offering you has this value for this transistor, maybe a femtofarad by 10 femtofarads per micron square, something like that. Okay? All right, so much for this capacitor. We now can relate it to dimensions of the transistor. Of course, we'll have to get more insight into what other characteristics these dimensions affect. Yes? C prime is a technology constant. It's much like when you buy light bulbs. You can buy light bulbs that have 80 watts or 100 watts or 50 or so. You can also get technologies, and they have different values for this C prime. So you get a manual, big fat manual, and it tells you, among other things, what this value is. Okay? And of course, there are trade-offs on how to set it, and it would be a fun lecture to talk about that, but I'd like to go on a little bit, and I'd like to get to this part here. Okay, so here just, when you make a transistor, you get a capacitor. If you know a way on how to make a transistor or something equivalent that does not have this capacitor, you're a rich man or woman, okay? Nobody has figured out how to do that. The other thing is this resistor there. Hey, if we have a switch, we sure do not want a resistor, but in practice we get some resistance. There is no superconducting. Well, I guess there are superconducting transistors if you like to live at 2 degrees Kelvin or whatever, and they have all sorts of other problems. So in practice, we don't use those much. Yes.
So how do you change the switch?
How we change the setting of the switch is simply by changing this voltage here. We need to change the voltage between here, that gate, and the channel. And fortunately, it is, even if we change the voltage between this terminal and the terminal that's attached there on the side, then we control whether there are electrons available here to carry charge or none, or somewhere in the middle, right? That's how we control it. Yeah, it's a good question. Okay, so that's how we control the switch. So now when we put a lot of voltage there, for example, VDD, then the switch is on, but we still have a residual resistance, and that resistance we model simply by this component here in our equivalent diagram. Okay? Now, how big is this resistor? Well, it's written here. Again, what would be the ideal value? Well, we really don't want a resistor. When the switch is on, there should be no resistance. But once again, hey, if you know how to do that, great for you. Send me a postcard. Okay? You can also send a check to the university. Okay, so this resistor, well, if you look again at this picture here, it's a little bit like a tunnel. If the tunnel is very, very long, well, it really slows down the traffic, right? And so if the length of this channel is very long, well, the resistance is going to be large. So the resistance should be proportional to L. And when we go and measure it, lo and behold, it is. Okay? And, well, again, if you make the tunnel wider, well, then more cars fit through, and so the resistance that they see is smaller, so the resistance should be inversely proportional to the width. Wider highway, more capacity. And then again, there is some proportionality constant that depends on the technology. It also, and we will look at that later, it depends on the value of VDD. If you make VDD larger, not too surprising, we get a stronger field effect, and consequently the value of this resistance gets smaller. But that's what it is. So ideally we would like both of these to be 0. That's what we would like. Now, very often, if you're a circuit designer, then you're mostly concerned with exactly what these values are and so on. If you are a manager or so, or an inventor, and you design something new or so, then you want to be able to compare new technologies. You want to be able to determine whether a technology has the capabilities that you need. And how do you do that? You don't want to go and design your entire thing in one technology, only to find out later that it isn't actually good enough. You would like to be able to compare these and say, this is the better one, and I'm going to use that one rather than this one here. So very often the way we do that in engineering is something called a figure of merit. Okay? We compare things based on ideally one parameter, and if that one parameter is bigger or smaller depending on how things are set, then we can determine what is better. Let's try to construct a figure of merit for transistor technology. So we have said already that ideally this capacitor should be 0. Ideally, it's not in practice, but it would be nice if it was. The same thing, the on resistance should be 0 if we could get it. So in practice, of course, there will be a trade-off, right? There will be some technologies that have a lower R1, but then a higher CG, and vice versa, right? So it turns out that the very useful figure of merit is really the product of R on times CG, because we want both of these to be small. We really would like this product to be small, right? This product ideally should be 0 again, but in practice at least we want the lowest we can get. And this product you will recognize, of course, is a time constant, so we call that tau. Okay, so actually tau on of our transistor. And now, remember, what was R on? Well, that was written on the previous slide. R on was L over W times R prime. So L over W times R prime. Okay. And then, what was CG? Well, again, we can check here. It was W times L times C prime. Okay, we can simplify this equation a little bit. The W's, wow, they drop out. So apparently if I make it wider, the transistor, well, the R1 gets smaller, but the capacitance gets larger and the tau stays the same. So this figure of merit actually is L squared times R prime times C prime. So R primes and C prime are again technology constants. And there are a little bit different constants for more or less. It turns out that if you go to different fabs, this product for a given technology branch is almost the same. Okay? But here, the length. So apparently, if I can make the length of my transistor smaller, I get a much better transistor. In fact, if I can cut the length in half, well, my transistor gets 4 times better. And now if you follow these news, right, again, IBM and Intel and AMD and so on, they compete with who has the best one and so on. They tell you, oh, we came up with a new process where this L is smaller. And that's why. So in fact, normally they make it from generation to generation, they cut L down by a factor of square root of 2. Why do they do that? Because if I cut this by a factor of square root of 2, then L squared is cut by a factor 2. In other words, the tau gets cut in half, and we'll see that everything goes twice as fast. Or we'll see it dissipates less energy. Okay. Yes. Last one? From the gate to the source, no. From the gate to the source, we have just a capacitor. No current is flowing. If you look at, it's just the control of the switch. There is no current flowing. It's just what controls the switch. Okay? Yeah. All right? So no current can flow into the gate because there is an insulator between the red gate and the blue channel. Okay? There's actually, usually it's silicon dioxide. What's silicon dioxide? Glass. Glass, right? Yeah. Yeah. So does glass conduct current? Well, no. Right. Actually, it is more tricky than that because if you make this thinner, you get better control. The field effect gets much more pronounced, much stronger. And consequently, one of the things people have made is they made this gap smaller and smaller. And now that gap is just a few, like 20 layers of silicon diode atom thick. Now, if you make it thin enough, at some point, even an insulator starts becoming a conductor. And it's a big problem. So at least for now, managed to get around this by using a new material, not silicon dioxide, but we use now something called hafnium. And with this hafnium, we can make actually a larger gap, and we still get good control of the carrier density in the channel. So we get still a strong field effect. But there are lots of interesting considerations like that. We won't quite get into all of this. Again, so the main thing to carry away is, and we will see that shortly, is how fast our circuits can operate is directly proportional to this tau, and that tau in turn depends on L squared. And that is really the reason why we keep making L smaller. Of course, we also fit more. The transistors get smaller, we fit more of them on a chip, and that's very useful also. But one of the main advantages is that when they get smaller, they get faster, or we will see we can turn that also into less power dissipation. And that's really, at this point, the main reason why we keep making transistors smaller, because, of course, you don't really need that many more transistors to make a CPU, but you would like it to dissipate less power. Right? Okay, so that's exactly what industry has been doing. When I was born, transistors they were several 10 micron big. They were still smaller than the diameter of a hair, which is about 100 micron, but nevertheless they were pretty big. And now, well, they are 30 nanometers or so. And you get some kind of a scale here, right? They are smaller than an AIDS virus, okay? And they're much smaller than a red blood cell. They're bigger than an atom. But we're really running into the problem that we're playing with single atoms in some of these transistors. When we make them, we are not taking, a huge chunk of material. We are literally taking a few atoms for parts of how we make transistors. Okay? Mind-boggling, right? All right. So incidentally, that's of course also a challenge. What are we going to do when the number of atoms that we use drops down to 1? How do we really go further down, right? So very interesting question. All right. We will talk more about this Friday.